Hi everyone, my name is Mr. V and I would like to once again welcome you to Physics 30. This is Unit 1, Momentum and Impulse. You can find it in Chapter 9 of your textbook. So below are several curriculum outcomes that I want you to be aware of. I won't read them in the interest of time, otherwise these videos would be huge, but you can read them below. That is all the things you'll be able to do by the end of this chapter. So, many situations and activities in the real world, such as snowboarding, fishing, and driving, involve an object gaining speed and momentum as it moves. Sometimes two or more objects collide, such as a hockey stick hitting a puck across the ice. What physics principles apply to the motion of colliding objects? How does the combination of the net force during impact and the interaction time affect an object during a collision? These questions and more are explored in the coming chapter. So, below here are all the things you're supposed to do in this chapter. So there's a momentum and impulse pre-assessment if you haven't done that. Okay, hit stop on this, go back to the workspace card and look at that, complete it, give it to your teacher, then you go and do the videos. Okay, anyway, so if you've done that, then there's 4 parts to Chapter 9. Okay, part 1 is momentum, and there's notes and practice at the end of every part. Okay, practice is just out of the textbook, so you can either use the textbook pages or you can use the pages I've provided in the workspace. The advantage of the workspace is that you can write all over these things, but the thing is, it is dense type, so you might just want to use loose leaf anyways. You know what, guys? I'm going to leave that completely up to you. So part 1, this part is momentum. Okay, part 2 is something called impulse. Part 3 is collisions in 1 dimension. Now, those 3 are pretty straightforward. Part 4, collisions in 2 dimensions, that's going to be a long video. Going to warn you guys right now, lots of nitpicky little things. Not a big deal, okay? Just take it slow and we'll get through it together. All right, at the end of the 4 videos, okay, you have the momentum and impulse formative assessment. Now, what that is questions like review questions. They're not for marks. They are just for you to practice. Okay, the answer key is given in the workspace, so you can kind of mark your own stuff, just kind of see where you're at. Okay, the next thing is what's called a curriculum review. That is a summative assessment that does get marked. So it's all long answer questions. You go, you do them, hand it into your teacher, and you get a mark for that. Then, of course, you have a quiz, which is another summative assessment, so it gets marked. Okay, and at the end of all of those, you will have the momentum and impulse unit exam. Now, our unit exams, we have designed those to be very diploma exam-like. There's multiple choice numeric response questions, and they have the same kind of rigor as diploma exam questions, and some of them are our old questions that we've modified, that kind of thing. So just to basically prepare you. So anyways, that is kind of the outline for this unit. So let's get started. So part 1, momentum. Momentum is simply a measure of a quantity of motion that remains constant when objects collide. It is the product of the object's mass and its velocity. Okay, so the symbol is P, and it's a vector, so it's got that little arrow on top. Now, you're supposed to write the little arrow every time. Now, every now and then you forget and whatever, but you are supposed to put that. Okay, so P equals M times V, right? The product of the mass times the velocity. Okay, mass is measured in kilograms, V is measured in meters per second, so the units for momentum are kilograms dot meters per second. Wow, they really didn't get anything fancy for us there, but that's the unit for momentum. Awesome. Okay, so when you compare the momenta of 2 objects, momenta is just plural for momentum, okay, you need to consider both the mass and the velocity of each object. Although 2 identical bowling balls, A and B, have the same mass, they don't necessarily have the same momentum. If ball A is moving very slowly, it has a very small momentum. If ball B is moving much faster than ball A, ball B's momentum will be much greater in magnitude, that's size, than ball A because of its greater speed. Remember, if the object is just sitting there, it's not moving, so it won't have any momentum at all. Okay, so let's just kind of recap. Oh, sorry about that. Scroll down. There we go. Momentum is a quantity of motion. It's the product of the object's mass and velocity. It's a vector quantity. okay, due to the object's velocity. Okay, remember the vector means it has size and direction. Okay, it's represented by the symbol P. Okay, it has units of kilogram meters per second, and it is 0 for an object at rest. Okay, I want you guys to consider the following questions. How would the momentum of an object change if? What if we double the mass, but the velocity stays the same? So here, let's just write this down. So, gotta get the pen back. So P equals mv. Now, if I take the mass and double it, I'm going to end up with 2m times v. Okay, well, if I have 2m times v, what's going to happen to the momentum? Well, the momentum, this number, this part is the momentum, it's going to get twice as big. So if the mass is doubled, but the velocity remains the same, the P doubles. Okay, it's a direct relationship. Okay, or direct proportionality. Okay, so momentum doubles. Okay, if the velocity is reduced to 1/3 of its original size, original magnitude, but the mass stays the same. So again, if we start with P equals mv, but now we take the velocity, leave the mass the same, but take the velocity and make it 1/3. Okay, if I just do some rearranging, the number just goes out in front, so 1/3 mv. Now remember, mv is just the original momentum, so it's 1/3 of the original momentum. So the P, the momentum, is 1/3 of the original. Okay, so again, this is proportional. If the velocity goes down by 1/3, the momentum goes down by 1/3. Moving on. Okay, the previous questions are called proportionality questions. We can use proportionalities to solve momentum problems. These questions occur in every unit in Physics 30 with any concept that has a formula. So, funny, pretty much everything. This fact makes the following skill very important. Okay, so we can solve problems using proportionalities. So consider an object that has a constant momentum of this, 2.45 times 10 squared kilograms meters per second north. Okay, that little bracket thing with the n, that means it's going north. Okay, awesome. Okay, determine the momentum of the object if its mass decreases to 1/3 its original value and an applied force causes its speed to increase by 4 times in the same direction. So here's how I'm going to teach you guys to do this. Write the original formula first. So P equals mv. Okay, so our new momentum, or our old momentum, so P is 2.45 times 10 squared. Okay, well, really, that's just 245. It's not a big deal. If our sig digs work, we don't actually have to use scientific notation, but that's okay. So mv. All right, so now let's write the equation again and put in all the stuff. Okay, so our new momentum, and we could write new underneath that if I really wanted, but it's not a big deal. Okay, so let's see, what did we do? We took the mass and decreased it by 1/3, so we have 1/3 m. Okay, and then some kind of a force made our speed increase 4 times, so now I've got 4v. So now let's rearrange, or combine the numbers. Okay, so 1/3 times 4 is just 4/3, or 1.3 repeating. Okay, and then look at this. So then the m and the v go together. Well, funny, I know what the m and the v equals. M times v is 2.45 times 10 squared. So really, I can just substitute that, and we go 4/3 times, well, this mv is 2.45 times 10 squared kilograms meters per second. Okay, and we're not going to put the north in until the very end. Okay, so this works out, so you just multiply this on your calculator. So you end up with 327. Now, that still fits in our sig digs, so we can just write 327. If you really want, you can go 3.27 times 10 squared. Okay, kilograms meters per second north. Okay, put a box around that because it's really nice for me to see exactly what it is you guys want me to mark. Okay, so 327 kilograms meters per second north. So if we write it in 2 steps like this, we can always do that little substitution with the MV, and then we just multiply it by whatever that number works out to be. It's pretty nice, pretty straightforward, and like I said, this will happen in every unit in Physics 30. Okay, so the next little bit, I want you to imagine yourself in these situations to help you understand the concept of momentum, which of course is mass and speed, mass and velocity. So imagine yourself catching a baseball at 5 meters per second, so a nice gentle toss. Okay, now imagine yourself catching a medicine ball, which is like 3 kilograms at 5 meters per second. Okay, so a little baseball, big medicine ball, which one is easier to stop? Okay, well, it's easier to stop the baseball, right? Okay, the baseball, why? Well, it's smaller, it has less momentum. Okay, try this one. Catch a tennis ball at 5 meters per second. Now catch the same ball at 50 meters per second. Which one is easier to stop, or which one, hurts less? Okay, the tennis ball at 5 meters per second, the nice gentle toss, that's awesome. Like that's pretty easy, it's not hard. Okay, 50 meters per second, okay, that hurts. Ouch. That is really, really fast. So assuming you can catch that, it would probably hurt your hand. Okay, so which one's easier to stop? Obviously the tennis ball at the slower velocity because it has less momentum. Okay, so those answers, okay, help with the idea that mass and velocity are both really important parts to momentum. Great. Okay, so let's do some examples and see if we can make this work. Okay, so a golfer putts a 45.7 gram golf ball at a velocity of 1.50 meters per second west along a level green. Okay, determine the golf ball's momentum, assuming the velocity remains constant. Okay, easy enough. So remember, P equals mv. Now, little tiny funny thing here is you'll remember that the mass has to be in kilograms. So to get the grams to kilograms, we have to divide by 1,000 or move the decimal place over 3 spots. Okay, either way, it is 0.0457 kilograms. Okay, that's a big deal. All right, so our momentum is 0.0457 kilograms times 1.50 meters per second. Now again, I'm not going to put the west on right here. I'm going to wait till the very end to figure that out. Okay, so we just type that into our calculators and we get, so 3 sig digs, yes, everything has to have sig digs. So 0.0686 kilograms meter per second, and now we put in the west. So we can put in the whole word or just W, put those little funky square brackets around it just for the direction, and put a box around it. Awesome. Okay, so there is our answer for that one.
All right, number 2. A 273 gram bird is flying at 12.9 kilometers per hour at 316 degrees. Determine the bird's momentum and use it to draw a momentum vector diagram. Okay, so first things first, we notice that we have 273 grams, so that works out to 0.273 kilograms. Okay, and then we have the 12.9 kilograms per hour. We have to turn that into meters per second. So 12.9 kilometers in 1 hour. Okay, so we use that. We know that there are 1,000 meters in a kilometer. And we know there's 1 hour and 3,600 seconds in 1 hour. Now I've arranged them like this. This is you did this in Physics 20, so the hours cancel, the kilometers cancel, so you're going to be left with meters per second. Okay, and when you do that, you end up with 3.58. It's actually 3.583333, 3.58 meters per second. Now, the easy way to do this is just to divide by 3.6, okay, and that works. I'm going to leave that up to you. So of course P equals mv. So we know that the mass 0.273 kilograms times 3.58 meters per second. Okay, so that works out to, when you multiply those together, we end up with 0. We've got 3 sig digs, so 9, whoops, that's not a 9, that's a 9, 978, okay, kilograms meters per second. Okay, so when we work this out, what ends up happening, or sorry, that's the answer, I guess, is 316 degrees. Okay, so when we draw the momentum diagram for this, remember 316 degrees goes this way. So 316 degrees is about there. 316 degrees, and then we just put our momentum on. So 0.978 kilograms meters per second. And we already have the angle on that, so that is cool. Now remember, we also, there's other ways of representing this. So we could have, 360 minus 316, okay, is 44 degrees, so that is a 44 degrees in there. So we could also say that this is 44 degrees, okay, and that is going to be south of east. Okay, and there's a 90 degree relationship here, so we could always do this angle. So 90 minus 44 is 46. So 46 degrees east of south. So I could use those, that kind of measurement as well, the navigator system. So if you prefer, you can do that. All three are correct. But for this, because our answers, or our question was asked in the 316 degrees, we should have that as part of our momentum vector diagram. Okay, so that's that one. Alright, number 3. Use the graph of momentum as a function of speed to determine the object's mass. Okay, so we're going to look at this graph, and the first thing we notice, okay, momentum as a function of speed. Okay, and then on the side it says momentum, and then times 10 to the 3 kilograms meters per second. So whatever number we choose for this, we're going to times it by 10 to the power of 3. Okay, not a big deal. Alright, so the first thing we want to look for is we want to look for where the line crosses a perfect point. Like, that would be awesome. Now if we look at this graph, okay, like that one's close, this guy here, but the line is clearly above the crosshairs. Like, it's just above. So that's not quite what we want. And then over here, this guy, he's kind of close too, but he's not perfect. So I guess what, long story short, is there's no perfect points on this graph. So barring perfect points, we look for perfect half points. So a perfect half point would be kind of like this. Okay, and the reason that's a perfect half point is because it's perfect on one axis and it's exactly halfway in between on the other axis. So then all we have to do is count the points. Okay, so first of all, momentum and speed. So remember, P equals mv, right? So the thing is, if I want my mass, the mass then is the momentum divided by the velocity. Okay, no worries. So my momentum, so let's see, there's 2, 4, 6, 8, 10 is there. So 10, 12, 14. So this is halfway between 14 and 16. So that is 15.0. And then again, times 10 to the 3. Okay, kilograms meters per second, and we can just type it in just like that. And then the speed, okay, 2, 4, 6, 8, so 10 is there, so 10, 12, 14.0. We just use the same sig digs as what they've got, so 14 meters per second. Okay, so when we divide that out, we end up with 1,250. So to 3 sig digs, that is 1.25 times 10 to the 3 kilograms. Fantastic. Now, the important thing to note on these graphs, or an important thing to note, is if I use another point, like that's pretty close to a half point. Like it's a little bit off half, but you can still use it. And depending on your estimating, you might get a slightly different answer. It's not a big deal, right? It's they'll still be very, very close or in the same ballpark, but because we're using points on a graph and our own discretion, answers for these can be slightly different from one another. It's really not a big deal. Okay, so we'll move on to the next one.
Number 4. A 65 kilogram girl is driving a 535 kilogram snowmobile at a constant velocity of 11.5 meters per second at 60 degrees north of east. Okay, calculate the momentum of the girl snowmobile system. Okay, well, what we do there is we just add up the mass. So 65 and 535. Okay, that works out to a nice even 600 kilograms. Okay, so if I want the momentum equals mass times velocity. So 600 kilograms times 11.5 meters per second. Okay, again, we're going to leave the direction out of there for the calculations. So when you type this in, okay, 600 times 11.5, that works out to 6,900 and some. Okay, it's a big number. Okay, and you've only got 3 sig digs. Okay, so what we do, remember we stuff these into scientific notation. So 6.90 times 10 to the 3. Okay, and you have to do it that way. This is not new, it's physics 20. Okay, 6.90 times 10 cubed kilograms meters per second. This is where we put the direction. So 60.0 degrees north of east. Okay. There we go, and that is our final answer. Then B, draw the momentum vector for this situation. Okay, so remember, if we draw an axis set here, so this is north, okay, east is over here, west is over there, then south, of course. So if I am north of east, remember this of part, north of east, so I am north of the east line. Okay, so here's the east line, so I am to the north of it. So I go like that. That's how we draw our picture for this. So that is 60.0 degrees north of east. Okay, and then of course our momentum goes on that, so 6.90 times 10 to the third kilograms meters per second. And that is how you do that. Okay, last one for this section. A car has a momentum of that if the mass of the car is reduced to 2/3 of its original mass, but its speed is now 9/4 of its original speed, determine the new momentum of the car. So this is one of those proportionality ones. So how I taught you to do this, we write it once, P equals mv. Okay, and we know that our momentum is 7.9 times 10 to the 5th kilograms meters per second. Okay, awesome. That equals our mv. Perfect. So now we have the new momentum equals our new stuff. So the mass of the car is 2/3. So 2/3 mass. Okay, and the speed, or so times, the speed is now 9/4. So you get 9/4 v. Okay, so when you have two of these numbers, okay, we're going to multiply those. So when you do that, you end up with 3 halves. So 2/3 times 9/4 is 3 halves. Okay, and then of course mv. Right, so 2 times 9 divided by 3 times 4. Reduce any way you want. Okay, that's you guys can figure that out. Okay, now again, the old mv, that part there is this, the 7.9. So this is 3 halves times 7.9 times 10 to the 5th kilograms meters per second. Okay, and you just type that into your calculator, keep the sig digs the same, and you get 1.2 times 10 to the 6th kilograms meters per second. Please notice how they did not put a direction in the original, so we can just assume that we're in the same direction as before. Okay, so 1.2 times 10 to the 6th kilograms meters per second. Awesome. So guys, I want you to practice this material by completing these questions. So in your textbook, it is page 453. I would like you to do numbers 2, 5, 9, 10, 11, 14, and 15. Again, you can do that right from your textbook with loose leaf, or you can print the document in the workspace card, and then you can write all over right beside the questions. Either or, I'm going to leave that part up to you. Good luck, and we'll see you next section. Thanks.